So, okay, I'm doing continue. So, you want me just to start?
Yes, please. Yes, I think yes.
Oh, okay. So I will start. I'll share my screen in just a minute. I certainly would like to first say it's wonderful to see all the names on this screen. And I know many of you, I'd love to see more of your faces, but I recognize your names and I'm just delighted to be associated with you. So I'm going to start sharing the screen. I hope it's going to work. Ah, there. Okay, does it show up okay?
Yes, perfect. Yes.
Okay, so this is an overview of density functional theory, but I'd like to start with the subject of assessment, electronic structure. Electronic structure really is the challenge of a many-body interacting electron problem, one of the great challenges of physics. In addition to being a great challenge for deep insights in physics, it has important applications. It has consequences for essentially all areas of science and technology because it's become so useful. But if you want to do things that are really relevant for science and technology, it has to be quantitatively accurate at some level. So the question is, how can we possibly expect to calculate properties accurately when it's such a difficult problem? The great advance was density functional theory. To make a few comments on just density functional theory before proceeding, it's based on profound ideas and inspired choices that have made it so powerful. My goal is to give some background and the ideas of how revolutionary was the approach of Cohn, Hohenberg, and Sham for this problem. And I'd like to make a couple of general comments. In my opinion, the key to success for DFT is to divide the problem into two parts. Finding the functionals that are so useful, or rather finding the functionals and approximations that have turned out to be useful, and using the functionals. A lot of smart people have worked on both aspects of this problem, and it's because one can divide the problem that it has been possible to make such progress. Each of these is challenging and rewarding, and because of this great success, codes that use functionals have been developed that are very powerful, like quantum espresso. Tutorials in this school about how to use quantum espresso and similar codes. So I would like to emphasize, it's not essential to describe all the details of the functionals. In fact, it's kind of too bad that you can just jump in and do calculations without understanding much. That's not good. It is essential to appreciate the ideas behind the functionals in order to use them well. And the challenge for you is to use them well to solve interesting problems. So what are we going to work on? If you look in any book on solid state physics, you'll see the contents look something like this. Things that have to do with the crystal structure, the elastic constants, vibrations, and things that are called electronic properties like band structure, metals, insulators, etc. You've already been introduced to some of these, and there'll be much more in the rest of this school, but what we would know, everybody would agree that all this is properties of electrons and the presence of nuclei. Well, that's just, of course. But to do something about it, modern DFT calculations actually are most successful for the first part, structures like determining a stable crystal structure, the lattice constants, or phonon frequencies, or molecules, and the structures of molecules. Electronic properties turn out to be problematic, and we'll discuss more about that, and that will come up later in this school. So a bit of background for DFT. I think it's nice to get some history that sets up the background. So in 2 years will be the 100th anniversary of the first paper by Louis de Broglie that set in motion quantum mechanics as we know it. Within 2 years was the Schrodinger equation, the Pauli exclusion principle, Fermi statistics already. By 1928, the full relativistic quantum mechanics was worked out, then just the form that we use it today. The first density functional proposed by Dirac in 1928. And of course, Thomas Fermi approximation, it's rather crude in many ways, but it was a density functional approximation. And the Bloch theorem for states in crystals was already in 1928. In the 20s, there were, it's really impressive that there was calculation by Hilarius for essentially exact calculation, numerically almost exact, for 2 electron problems like helium and hydrogen. This is a difficult problem because of the interaction between the electrons, and we'll say more about that later. At the same time, there were developed methods, particularly by Hartree as first, and then Hartree and Fock, for numerical solutions for electrons in atoms that could be much more than 2 electrons. But the simplification was that each electron is moving independently on an effective potential. So you've given up having a direct interaction between electrons and replaced it. And of course, the idea is, how good is that? Well, let me write down, in order to establish my notation, the independent electron problem, which is just the Schrodinger equation for 1 particle in 3 dimensions. If you have many particles, it's the same equation. It's just that if they're fermions, you have to occupy the states, the lowest states, the lowest energy states, which is with with the number of fermions that you have, and the density is just a sum of the occupied states with the wave function squared. The total energy is similarly a sum over the expectation values of the Hamiltonian, which is just the sum of eigenvalues. And it's useful to write it out in the form at the right, which involves the kinetic energy and the interaction of the electrons with the potential. And notice how simple this is. It always has the form of just the integral of the potential acting on the electrons and the density. I've written the effective potential because the question in actually using this is, what potential do you use? If you want to describe some complicated system, in general, you have to come up with the effective potential. So, and for crystals, you've heard lectures by Shobana earlier today for the notation that's needed for a crystal would be the wave function and the label by the band index and a momentum index. That's the Bloch theorem. But I'm going to just label the states by I like this in order to just keep it very general, and it will apply to crystals as well. So already in the 30s and 40s, very much had been done by some very good people. Hartree-Fock method. Wilson is the one that stated most clearly the implications of band theory, dividing insulators and methods, and for the metals for the first time in the 1930s to really understand the differences in properties of materials like that. there were quantitative calculations by Wigner and Seitz and Slater and others. These pseudopotentials were already developed in the early 30s. The first understanding of semiconductors was being worked out. And all this was done using independent electron approximations, but very cleverly choosing which independent electron problems you were working on. And I have a little interesting addition. Two of the people that were involved in the invention of the transistor were Bardeen and Shockley. Bardeen was a student of Wigner, and his thesis was Fermi surface of metals. Shockley was a student of Slater, and his thesis was calculating the electronic bands of sodium chloride. So people in this business made important contributions. And by the 50s, the first big computers were around, and perhaps the first application that was to the bands of germanium. This is still using an independent electron approximation because the computers were nowhere near the point of attempting to do the many-body calculations. Here's a nice story that I got directly from Frank Herman. His mother had done calculations with a hand calculator before, and when he did the calculations on the computer he was at IBM, by the way. He said he found that his mother never made a mistake. So what about the original problem? The original problem was this grand challenge of interacting electrons. How do we actually approach that problem? So why is the problem hard? The solution by Hilleris in 1929 was a tour de force, but one can think about the basic problem that with two electrons, each in 3 dimensions, it becomes a 6-dimensional problem. And he was able to solve that by a variational technique. But what if we have 3 electrons, 9 dimensions, 100 electrons, 300 dimensions, 10 to the 23rd on the solid? What do we do? The difficulty scales exponentially with the number. Clearly, you have to just adopt a different idea for the solid, but in chemistry or when you're looking at small molecules, you can really imagine just doing the calculation, but the exponential kills you. Today, one might do an exact calculation for 11 electrons, which is a huge calculation. And tomorrow, maybe a few years, you can get up to 12. So this is a hard problem to address directly. There was some landmark work that occurred in 1964 and 65. One of them was the density functional theory. This is what we talk about in the rest of the lecture, and it is what's become the method that has had such a great effect. It's interesting that the same years, the other methods of dealing with quantitative calculations for solid were developed, with Hedin's GW approximation in 1964, and the first quantum Monte Carlo simulations of many-body systems by Macmillan in 1964. By the way, he was a student of Bardeen at the time and did calculations on computers that he put together in his basement. So let's address the problem of interacting electrons. This is a full Hamiltonian. It corresponds to kinetic energy of the electrons. The operator is the same as for one electron, but the final effect is very complicated for the kinetic energy of a correlated electron system. The electron nuclear reaction is just the Coulomb interaction, and the electron-electron interaction is Coulomb, and simple to write down. But one thing we can notice already is that these two are similar orders of magnitude. The electron electron interaction just cannot be neglected in anything that approaches quantitative accuracy. The terms below involve the nuclei directly, and only one term in this entire formulation is small, and that's the kinetic energy of the nuclei. And we just set it to 0. We fix the nuclei for the purposes of developing density functional theory, and then they're the static external potential, and the external to the electrons is something that the electrons feel. And later one can put it in by perturbation theory if you wish. The other term is just the interaction between the nuclei, which is basically just a classical additive term that can be included or not. And it's just always additive. And the essential problem is the top line, interacting electrons in an external potential. The external may mean the nuclei, or it may mean other kinds of potentials applied to the electrons. So what did Hohenberg and Kohn do in recasting this problem in a different form? Here's the equation again. But what Hohenberg and Kohn did was to focus not on the Hamiltonian itself, but on the energies. The first term, the kinetic energy, then the integral over all the particles is called the total kinetic energy, given the label T. And the interacting electron, the problems due to interacting electrons is called the interacting contribution to the energy. And the external potential is a simple form that it always has in all problems, just the density times the potential integrated over all space. And the beauty of this separation is that the first two terms contain all the hard parts. The kinetic energy and interaction energy of the electrons, and the other terms are simple terms that you can evaluate easily once you know the positions of the nuclei and the density. So let's look at this a little bit more closely on the next slide. Oh, I've already said that. This is the difficult part, and this is the part you can just see immediately how to deal with. So the important thing about this division is that not only is everything difficult put in this place, but it must be universal. It's the same functional for all systems. The only way the only way the electron knows which system it's in is by which potential is applied to it, like where the nuclei are. So what does a universal functional mean? The square brackets is a notation for functional, and it means a value that's returned that depends on the entire function, in this case, the density. So it must be universal because everything in here involves only the electrons and has nothing to do with the values have to do with the external potential because the density is a functional of the external potential, but the sense in which they depend on the density must be universal. Now, I've jumped to the final conclusion of Hohenberg and Kohn that it is determined by the density, but let's look at that. We know that this energy is a functional of the external potential. The external potential is just the variable in three-dimensional space. And we know that it determines everything because you could solve the Schrodinger's equation. So it's obvious that it's a functional of the potential. But the proof that it's a function of the density is what Hohenberg and Kohn did. Really, in the end, it's just the transformation of variables. Call it a Legendre transformation from variable called potential to a variable called density. It's actually the same thing that you do in thermodynamics, like for solid under pressure. You can view it as a complex system with all the stuff going on down inside, but the energy can be considered as a function of the density or the pressure. And you can make transformations between one and the other. The proof that Hohenberg and Kohn gave was special to the problem of many-body interacting system. And the proof was that for a given density, there's only one potential that could give that density as its ground state. Or in other words, there's only one potential that goes with the density. The density determines the potential. And the potential and the density determines everything by that logic. But the theorems give you no hint as how you could actually calculate anything except by solving the Schrodinger's equation. We're just back to where we were in that sense. It has some elegant ideas behind it, but up to this point, nothing is given that tells you what you might do. Now, was that worth a Nobel Prize? The thing that got a Nobel Prize was realizing what to do with that information, what to do with that construction of density functional. And that was the Kohn-Sham auxiliary system. This was the ingenious idea that really deserved the Nobel Prize. The idea was to invent a new system, an auxiliary system of things that you might call electrons. They have the mass of electrons and the charge of electrons for how they interact with the nuclei, but they don't interact among themselves. So this is the auxiliary system. And since these particles don't interact with themselves, then it becomes a soluble independent particle problem. In this setting up the problem for this auxiliary system, there's an additional term in the energy called the exchange correlation energy that takes into account the effects of interactions as far as the ground state is concerned. It's not guaranteed that you get all properties, but you're now focusing on the ground state. And the result is the density of the ground state and the total energy of the ground state of the interacting electron system. If you had the exact functional for exchange and correlation. So strictly nothing else is supposed to be given by this approach. By focusing only on the ground state density, it has been possible to make a theory that's actually practical, as opposed to work that the other many-body methods that we're trying to solve the problem directly and calculate other aspects other than just the ground state density and energy. So the formulation is exact in its form. If you knew the exact functional, you get the exact answer. In practice, you don't know that, and it's probably one of these unknowable functionals. But in practice, what it did was make possible useful approximations. So let's look at the way this was formulated by Kohn and Sham. The idea was to set up a system of independent particles so the kinetic energy is just the sum of the wave functions of del squared operator expectation value. The density is just the sum of wave functions squared. The Hartree and the interaction term has now been divided into a Hartree term, which is nothing more than the energy as if the electrons were just a smeared continuum of density called N. And that's an example of a functional of the density that you can write out very explicitly. There's just the Coulomb interval of the product of the densities at 2 points. The ion term, that's depends on the nuclei, that's just the additive term. And everything else, the fact that the electron's kinetic energy is not the same as independent particles, the fact that electrons are correlated with one another, and this is not the interaction energy. It's buried in this functional called EXC. So we now have sets that we believe will be soluble because they're just independent particle expressions, and everything difficult buried in this exchange correlation term. As we've said, that's unknown. If it were possible to get the exact functional, you'd have the exact answer. But what it really did was just a new paradigm for how to deal with many-body systems, find useful approximations for this functional. And how do you actually deal with it? The way that, since it was oriented toward the ground state, the appropriate approach is to minimize the energy with respect to all the variables in the problem. In this case, the variables are the independent particle wave functions for these for this auxiliary system. And the idea is that you would minimize the energy with respect to all these wave functions. And this has to be done with the constraint that the different wave functions are orthogonal to one another, since it's a fermion problem. And this leads directly to the Kohn-Sham equations with a kinetic energy operator that's like in a Schrodinger equation, a potential, and writing out the Schrodinger equation in this form, it's the eigenvalue times the wave function. So now, back in the independent particle methods, we mentioned that where does the potential come from? Well, the Kohn-Sham construction gives you a very explicit way of constructing that potential. It applies to the auxiliary system, just to be sure, but we have a way to determine it if we know what this functional is. In doing this variational minimization, the key thing is that's involved is the density. And you can use the chain rule to calculate the effect of all these potential terms that involve the density by take the derivative with respect to the density, and then the derivative of the density with respect to the wave function, and you find that the potential is the external potential, the Hartree potential. That's very simple to calculate once you know the density, and the exchange correlation. That's also simple to calculate if somebody gives you the exchange correlation functional. So this is the Kohn-Sham equations that are self-consistent in the sense that you have to put in the potential to solve for the wave functions. The wave functions give you a density, but the potential itself depends on the density. So it becomes a self-consistent problem that's iterated to solution. And this is the kind of thing that's done in the marvelous codes that do this so efficiently. At the right are noted as a very important point that in the Kohn-Sham problem, the eigenvalues and eigenfunctions are just auxiliary functions, and they don't have a direct physical meaning. So we'll come back to that later. So what is the exchange correlation energy? If the electrons were independent, then you just add up the eigenvalues. The difficult part of the problem is that each electron really is not independent of the others. There's a reduced probability of finding other electrons near each electron. And this is called the exchange correlation hole. This is the difference from just this average density calculation that's called the Hartree energy. The real system must take into account that the exclusion principle pushes other electrons away from each one because two electrons cannot be at the same point. And I'm ignoring spin for the moment, but we can always say this more properly with with spin saying that that its electrons are the same spin that have to obey the exclusion principle. And correlation affects electrons of both spins, that electrons are pushed away from one another by Coulomb interactions. So these little diagrams at the bottom are just meant to be contour plots of the reduced probability of finding electrons nearby a given electron at the point indicated by the dot. So here would be an isotropic system. Here's an anisotropic system. You know, real anisotropic systems might be much more complicated, but the key is that the energy depends only on the spherical average, or A key. So let's see what kind of functionals have been developed. Now, I'm really not going to say much about these. There's more said by lectures later by George Amolo and Karsten Ulrich. But I want to name some of the functions and describe a little bit of what they are. One approach is to use a model system where you can really deal with a many-body problem. Like the local approximation is to use what you know about the homogeneous electron gas. This has been calculated in great detail by quantum Monte Carlo calculations of Separately and Alder, and then assume that the functional is the same in an actual system that's not homogeneous. That would be, pick up any system and say at any point you have a density of electrons, and at that point you'll say that the exchange correlation is the same as if electrons of that were in a homogeneous gas of that density. The gradient approximations are another model system, and one of the ways of approaching it is also using Monte Carlo calculations that are done for systems that have spatially varying densities. There's many other developments, and many more recent ones use theory in somewhat more direct way to approach the problem, not just taking something from a model system, like hybrid functionals, Van der Waals functionals that are able to treat interactions that are quite non-local. And these are described more in the other lectures. So here's my little example that I particularly like that's due to Gunnarsson and coworkers from the 70s. Suppose you consider a neon atom. Oh, brother, I didn't mean to show that. Ah, right. I wanted not to show that right now. It's about as far from a homogeneous gas as you might get, with a huge gap for excitations and a very inhomogeneous density. This figure is a little bit hard to understand. This is for electron at points at a chosen point near the nucleus, which is sitting here at the blue arrow. This red arrow should have been exactly on 0. And that would indicate that at that point there's a given density for in neon, and at that point you would say that the exchange correlation energy is the same as if an electron was in a homogeneous gas of that density. Now the real exchange correlation hole is the effect on other electrons if an electron is at this point. And it's very asymmetric. The other electrons are back near the nucleus and very few out further. And so the exchange correlation hole is mainly back near the nucleus. If it is a homogeneous gas, of course, it's symmetric. And whether you go to the left or the right, it's all the same. Now, would you consider this local density approximation, the dashed line, to be a good approximation to the actual exchange correlation, the solid line? Probably not. That doesn't look like a very good approximation. But if you take the spherical average, which is what's important for the energy, look at the comparison. It didn't matter that it was so asymmetric as far as the energy was concerned. If you look at the spherical average, the homogeneous gas is remarkably close to the neon atom exact exchange hole. This supports the local approximation very much. And just to be clear, it supports the local approximation for the ground state energy. It didn't necessarily support it for anything else. Furthermore, it also shows you what's not given by the cone-sham solution. It does not describe the actual correlation. It has only information that's embedded in the functional, and it does not describe the actual correlation or the actual exchange correlation hole in the system. So I've given some comments on the various aspects of DFT calculations that I consider particularly important. The properties of crystals is that you can think of as a test of density functionals. Like, for example, the lattice constant of silicon. We know it from experiment, and it's a test of how good a functional is. Nowadays, the calculations can be done to essentially arbitrary accuracy using computers. And so it's a test of the theory. Does the local density work or doesn't it? Does the GGA work or doesn't it? On the other hand, there's a very different use of DFT calculations because they're so powerful. Complex systems, the experimentalists don't know exactly what's going on. Nowadays, the theoretical calculations of playing a critical role right alongside experiments working together, giving understanding, predictions, simulations of things that are going on. Examples that for which this applies are surfaces, interfaces, defects, materials that are at very high pressure, thermodynamics, systems, liquids, complicated systems like interfaces that are buried, which is very difficult for experimentalists to study. So let me give you two examples. One is the first that I know of that really set this field in motion in a practical sense. I think this is the first calculation that was convincing that the density functional theory really can do something useful quantitatively. This is a set of transition metals, the 3D transition metals, the 4D, calculating the density, which is actually this is proportional to the lattice constant, comparing the theory and the experiment, the crosses. The other properties shown here, the bulk modulus and the cohesive energy, are more difficult to calculate, and more sensitive, and so they don't agree as well. But they already show the basic features, and improved calculations later are somewhat better. But this set it up that this is a useful method. So many calculations have been done, as you know, and here's an example. I looked in Science magazine last week. I was trying to understand something about batteries that are so important for renewable energy. The first words of this article are, aqueous redox flow batteries could provide a viable grid scale electrochemical energy storage for renewable energy. These are things that might work for huge amounts of storage of energy, not your car or your cell phone. If you look down in this article, you see their density functional calculations indicate possibilities for This is just the little article that's describing the big paper that you can find online, or later in the issue actually. And it's just assumed that people will figure out and know basically what density functional means. And this is the method that we have for calculating quantitatively something about materials that work together with the experimentalists as they go along. I would like to emphasize this point that I've already said. There are lots of methods. Plane waves is one, pseudopotentials is one. So here's a set of calculations that use plane waves and norm-conserving pseudopotentials, ultrasoft pseudopotentials. This is the augmented plane wave method that takes into account the core electrons without making a pseudopotential. And this is a material that I collected some years ago, and it's been updated since then. But the basic idea is that you get the same answers with different approaches if you do it carefully. Pseudopotentials at that moment were not as accurate, but more and more the improvements have made them quite accurate, and you can deal with many different methods and be confident as long as you do the problem very carefully. There's one more great advance that's occurred. That was the Carr-Parrinello advance. 1985 was the idea of how to solve the Kohn-Sham equations, the quantum Kohn-Sham equations, and the classical equations for motions of nuclei all together as one problem. This just revolutionized the kind of systems that one could deal with. I was one of the people that did calculations on one structure and then go to a different structure and another structure, and it's days and weeks work for each structure. This method suddenly opened up the picture that you could just guide systems. You could deal with liquids. You could deal with simulations to find the lowest energy by cooling. You could find quenching the system. You could look at chemical reactions as atoms move. Perhaps most important, the exact methods that they proposed are not used much anymore, but what it did was to stimulate the development of very efficient methods. And quantum espresso is one of them. It's because of these developments that the calculations can be done so efficiently for large systems and produce so many very useful results. I've said it before, it's really a new relation of theory and experiment. Here's something I'm proud of. It's calculations that I was involved in back in the early 90s or late 1980s. It was like the first calculations of this sort. I think the biggest calculations had been done at the time by Julia Galli, who had previously worked with Carr and Parrinello, and we were using the Cray computers at Illinois. This is carbon at very high pressures and temperatures with a prediction of when would diamond melt? What happens under pressure? It was actually controversial at the time. And these are our calculations, and it's turned out that shock waves, including ones done in just the last few years at these giant laser facilities, agreed quite well with the first calculations and somewhat better with more recent calculations. But already the first ones that used the local density approximation really give the basic physics of the problem. And this has gone on in things like this work by the Parrinello group of polyethylene, which is such a important aspect of industrial production of using a particular reaction, which is still difficult to understand. So let's move on to the other issues. Improved functionals, and in particular, improved functionals that can get different properties of systems. So structures and images more accurately, and also as much as possible different properties. So this is called the Jacob's Ladder by John Purdue, who is perhaps the best known person for the development of functionals, starting with the local density approximation and the gradient approximations that are considerably more accurate. The other functionals like the hybrids and the LDA plus U, which I refer to as DFT plus U, which will be discussed later in this school. There's yet further developments that use the polarizability of the system itself to produce more information about the functional. And there's one in the middle called meta-GGAs that use a kinetic energy density as well as the ordinary density. So this is called the Jacob's ladder, as because that's the words from the Bible, as we climb up to the heaven of the exact functional. Anyway, I'm not going to describe this further, and there'll be more in the later lectures, in particular the more advanced functionals that described by Karsten Ulrich. One of the most famous problems that's called the band gap problem is the fact that Kohn and Sham eigenvalues are often interpreted even as physical bands, even though Kohn and Sham said, don't do it. Some cases they're just terribly wrong, and it's now gotten this name, band gap problem. And partly this is, well, here's an example. This is a whole bunch of materials plotted on a plot that's as a function of the experimental gap. Take one material and the experimental gap and various calculations for that one material. And the solid symbols are the local approximations or the gradient approximations, which are generally way too low. It's a famous problem, and among the most famous is germanium, which is a metal. It's so low that it's a zero. Mercury telluride even has a negative gap, which means that bands are out of order right at the band gap. The improved functionals, that's mainly hybrids, has so much success, is the shown along this 45-degree line. If a point was exactly on this line, that would correspond to the calculated gap being exactly the same as the experimental gap. And so we see that there's a lot of progress along this direction, but that's something to keep in mind, to be careful what you do. So conclusions. The Kohn-Sham density functional theory has revolutionized the theory of condensed matter. It's possible to do quantitative calculations for many properties. It's not everything. One has to be very careful to be sure what one is doing, but it's exceedingly useful. The part of the secret is that the problem was divided into two parts, with smart people working on each of the two parts. Because it's so useful, the codes have been developed that make it very useful, like quantum espresso. Now, what's the challenge for you? You can take the challenge to be one of the people that finds new functionals. You can take the challenge to use the functionals, and they're both great. That if you choose the second example of using the functionals, your challenge is to use them well, to choose good problems and to solve interesting problems in material science, chemistry, and many different fields using the methods and using your intuition, your abilities to choose good problems. Thank you.
Thank you, Richard. Thank you, Richard.
Okay, I'm going to stop sharing.
Wonderful lecture. So we still have time